this lecture, we're going to see how we can express compatibility equations in terms of stress. So we know that compatibility equations involve second-order partial derivatives of strains, such as partial derivative, second partial of epsilon x with respect to y twice, plus the second partial derivative of epsilon y with respect to x twice, is equal to the second partial derivative of gamma xy, engineering shearing strain, in terms of x and y. And so for isotropic stress-strain relations, we can express this equation in terms of stress. And in particular, now that we're into two-dimensional elasticity, we're going to look at this for plane strain. We do need our strains written in terms of stresses. So let's go ahead and do that. We can write it either in terms of Hooke's law, in terms of nu and e, or the Lemay coefficients. Let's write down both forms for now, and then we'll decide which one we want to get into. There will be a fair bit of algebraic manipulations in this lecture, so hang in there with that. I want you to see where it comes from as you work problems. Then you'll understand some of the limitations and assumptions that we've made in generating the equations that we're going to end up using. So epsilon x can be expressed either of these two ways, and epsilon y can be expressed in a similar way. If we do this in terms of the Lemay coefficients, I'll just write this one down. 1 over 2g, we have some symmetry in here, sigma y minus lambda over 2 times lambda plus g, sigma x plus sigma y. Gamma xy, then we can write down as 1 over g times tau xy, and for reasons that will be apparent pretty soon, I'm going to write this as 2 times 1 over 2g tau xy. Alright, so let's put these into the compatibility equation. So the first term we have is the second partial derivative of epsilon x with respect to y twice. All right, we have the 1 over 2g multiplying all three of these terms. So it's going to cancel out on all three of the terms that we have. So I'm not going to write it down. We're going to have the second partial of epsilon x with respect to y twice. It's going to be the second partial of sigma x with respect to y twice minus the second partial of the term I'm going to write down next, we have a lambda over 2 lambda plus g times sigma x plus sigma y. Well, I'm going to rewrite that in a slightly different form, and what we'll have left is Poisson's ratio after we get rid of the 2g, Poisson's ratio sigma x plus sigma y. So I'm going to borrow from this term as well. Right. In the next term, I have the second partial of epsilon y with respect to x twice. I'm going to have the second partial of sigma y with respect to x twice. And I'm going to have a minus second partial with respect to x of nu sigma x plus sigma y. And on the right hand side, that's going to be equal to 2 times second partial of tau xy with respect to x and y. Now let's group some terms together. I have the second partial of sigma x with respect to y, and I have the second partial of sigma y with respect to x. I have terms that are sigma x plus sigma y times nu. I can factor the minus nu out from both of those terms, and this is a del squared sigma x plus sigma y in 2 dimensions. Then, bringing this term over to the left-hand side, I have it minus 2 second partial of tau xy with respect to x and with respect to y, and equal to 0. Let's make a little room. We're going to take a look at equilibrium equations. So we're going to keep this kind of on the back burner for right now. But we have an equilibrium equation that looks like partial of sigma x with respect to x plus the partial of tau xy with respect to y plus the x body force equal to 0. We have another equation that looks like the partial of sigma y with respect to y plus the partial of tau xy with respect to x plus the y body force equal to 0. What I'm going to do, I want to introduce second partials into this. So I'm going to take the partial derivative of this with respect to x, and I'm going to take this equilibrium equation, and I'm going to take the partial derivative of that with respect to y, and I'm going to add them together. Alright, so I'm going to have a mixed second partial derivative of tau xy. I'm going to have 2 of them. I'm going to have a second partial of sigma x with respect to x twice. I'm going to have a second partial derivative of sigma y with respect to y twice. I'm going to have a partial derivative of the body force with respect to x, and a partial derivative of the body force per volume with respect to y. And that's going to be equal to 0 when I add them together. Alright, so if you notice in the equation that I had written down at the top of the page, I have this term, and it looks a whole lot like this term. In fact, I can solve for that term. I'll go ahead and write it down. If I bring this to the other side, I'm going to have minus 2 second partial derivative of tau xy with respect to x and y is equal to these terms that I'm writing down here. And it's important to understand that we are looking at 2D elasticity problems right now. Alright, so let's go back and let's look at this equation. So I'm going to have the second partial of sigma x with respect to y twice. I have the second partial of sigma y with respect to x twice. The contribution from the shear term, now I can write that in terms of the normal stresses. So I'll have a plus sigma x with respect to x twice, and a plus sigma second partial of sigma y with respect to y twice. I have my minus nu del squared sigma x plus sigma y, and then I'll have my body force terms, partial of body force x with respect to x, and a body force y with respect to y, and equal to 0. Now let's look at this a little carefully here. These 4 terms put together is del squared sigma x plus sigma y. I also have a minus nu del squared sigma x plus sigma y. And then I have these body force terms over here. Probably be a good idea to go ahead and review what del squared is equal to. Okay, so let's do that in 2D. The del operator is a vector we can express as the partial with respect to x, e hat 1, plus the partial with respect to y, e hat 2. It's an operator that's just sitting there waiting to operate on something. Del squared is the same thing as if we were to take del and dot it with itself, which is an operator that looks like the second partial with respect to x twice, plus the second partial with respect to y twice. So I'm just dotting those terms. And so what I'm saying is when I have the operator del squared operating on sigma x plus sigma y, what that is we'd have to algebraically expand that out. Algebraically, it's partial derivatives, but we'd have to expand that out. And what we would get would be the second partial of sigma x with respect to x twice, plus the second partial of sigma x with respect to y twice, plus the second partial of sigma y with respect to x twice, plus the second partial of sigma y with respect to y twice. So that's why when I see a grouping of constants like this, I can write down the quantity del squared sigma x plus sigma y. Now we do have a little bit more manipulations we can do with this expression. We have a 1 minus nu, a 1 minus nu that we can remove from the common terms and have 1 minus nu times del squared sigma x plus sigma y plus these body force terms that we have here. We can do some further manipulations on this. If we want to solve for del squared sigma x plus sigma y, then that would be equal to, well, we'd have a minus partial of x with respect to x plus the partial of y with respect to y, with a minus sign, over on the right hand side. And then we'd have a 1 over 1 minus nu. That would be multiplying both of those terms. If we want, we can take the negative sign out. We have a minus 1 over 1 minus nu, partial of x with respect to x, minus the partial of y with respect to y. Or, in terms of the Lemay coefficients, we have a minus 2 lambda plus g divided by lambda plus 2g, partial of x with respect to x, that should be a plus the partial of y with respect to y. And if we want to do the plane stress problem, we would do our substitution that we talked about last time. We would put lambda bar every time we saw lambda, but lambda bar would be equal to 2 lambda g divided by lambda plus 2g, or nu e over 1 minus nu squared. The point, though, is that if we look at this equation, what we have is on the left-hand side something that looks like del squared operating on something. It's sigma x plus sigma y equal to some right-hand side. Now this is a partial differential equation. It's the Laplace equation. With differential equations, you can solve for a particular and complementary solution. But if body forces are constant, then this looks like del squared sigma x plus sigma y is equal to 0. And even if it's for plane stress, with those substitutions of material constants, if the body forces are constant, then this also still reduces down to just del squared sigma x plus sigma y is equal to 0. This will be an important starting point for us. Now there's a couple ways we can use this. We can find solutions to this type of equation and apply the boundary conditions and see what kind of solutions we get. However, another thing we can do is if we have some assumed stress fields for sigma x and sigma y, we just plug them into this equation, del squared sigma x plus sigma y, and we can evaluate whether or not that is equal to 0. If it is equal to 0, then for constant body forces, isotropic materials, we have satisfied equilibrium and compatibility relations. Okay, that's worth writing down. Let's make a clean slide for that. So del squared sigma x plus sigma y is equal to 0. The restrictions that we had was that it was for an isotropic material. Constant body force in the x and the y, and the body force in the z is 0 or can be neglected. This can work for either plane stress or plane strain. And this is a statement of combined equilibrium and compatibility. We use both of those equations in here. So one thing that I often like to do on exams for my students is I can give you a stress field for sigma x and sigma y. And I can say, does it satisfy equilibrium and compatibility? Well, it's easy. You just add those fields together and evaluate del squared. If that equals to 0, then it does. And once more, it's worth writing this down again. This is a common mistake that I see. We need to write down what del squared sigma x plus sigma y means. It's where you take the stress field for sigma x and you take the second partial with respect to x twice and add it to the second partial with respect to y twice, and you do the same thing for sigma y, and when you add up all those second partial derivatives, if it equals to 0, then we have a solution for a plane stress problem or plane strain problem that satisfies equilibrium and compatibility. Now we can take a look at this equation and see that any constant stress field will trivially satisfy equilibrium and compatibility. Any first order stress field will trivially satisfy equilibrium and compatibility. So if you have some bending moment times x divided by some moment of inertia, for example, well, that solution, when we take the second partial derivative, that will go to 0, and so that will trivially satisfy equilibrium compatibility. When we get to higher order terms, sometimes it's trickier, but we can still use this to check for that condition.